So we developed this idea of the character table, and using it as a collection of the symmetry representations within the model. Anything that is in this point group is bound by these symmetry species. All right. So just a real quick review of this terminology. These are our symmetry elements. These are our symmetry species, right? Or these are our symmetry transformations, whatever you want to call it, within the point group. But these symmetry species, when you have something in that point group, they can only be transformed one of these different ways, right? Or a linear sum of these different ways. Okay, so any transformation within that molecule, within that species, is bound by these conventions. And again, the way we see it a lot is when we talk about transformations, such as linear transformations, or vibrational modes, or Raman active things, or rotations. And we're going to develop those using within this particular lecture, how we can extract out vibrational modes and the like in symmetry transformations. Okay, so but again, there's a couple little features that are hidden within this character table that we can talk about. We already talked about the order, so we can sum up all of these symmetry operations, and that is the order. And it turns out that the order is important for determining information, so we're going to remember that number. Again, on many tables, it is given as a little like H equals, so it's usually the symbol H, but not always. But you can always count them up: 1, 2, 3, 4, 5, 6, 7, 8. So this has an order of 8. Additionally, symmetry elements are grouped by class. All right, and so any symmetry elements that are effectively related, like a C3 rotation, a C4 superscript 3 and a C4 superscript 1, those two are related. Those are the same class, and so they're lumped together. It turns out that the number of irreducible representations, often given the symbol gamma, is the same as the class. All right. So, and the characters that we see, these are the characters, have certain rules that apply. It turns out that the sum of all the identity characters, the sum of all the vertical ones for the identity element, again, this is only for the identity, the sum of the squares of that is equal to the order. Again, we saw the order was H. We see that this is 1 squared, 1, 1, 1, 1. All of those squared would be equal to 4. 2 squared is 4. So the sum of the square of those is going to be the order. All right? Additionally, along any character, along any reducible representation, the sum of the characters within that reducible representation is going to, the sum of the squares of those characters is going to be equal to the order. All right, so 1 squared, 1 squared, 1 squared, negative 1 squared, 1 squared. You see, but that only totals up to 5, Dan. Well, you have to account for the class, all right? So this represents, there are 2 separate C4s. So this would be 1. This would represent 1 squared plus 1 squared. So that's 3 now. 1, 4. 1 squared plus 1 squared, 5, 6. And then 7, 8. All right? So going along the horizontal, the sum of those characters will equal the order. All right? So those fall out naturally from the representation. Additionally, there is one representation that's going to be totally symmetric, and it's usually in tables. It's usually the first one. All right. So this is a totally symmetric. Every operation produces a symmetrical result. All right. So that's just rules we can go by in our construction of character tables. Again, we're not going to construct character tables, but these properties allow us to do things later. So we're just going to do this for the one character table we've been playing with. So last is the orthogonality rule, all right, which is basically that the sum of the products of the characters within two different reduced representations, the sum of those will equal 0. And they cancel out. So any two, they're basically at right angles to one another within their matrix. Again, this drops back down to the matrix description for these. Again, this is something you'll learn about in group theory, and so enjoy. All right? But we can use this to find characters that are missing. All right? So this orthogonality rule is really simple. All right? So we can do that for this last one. Okay. One of the rules for the character table is that the number of classes, 1, 2, 3, 4 in this case, is equal to the number of reduced representations. Well, we're short one. All right, so we're missing one, and so additionally, we know that the sum of all of these will equal the order. So the order is 4. The sum of all of these has to equal the sum of the squares of all these has to equal 4. So we know that this last representation, whatever it is. So here's our table that we have reproduced on slide 36. And you can see that we have our 1 that is completely symmetrical. And we're missing 1. And we know that our missing 1, so this is our missing 1. Question mark. So the product of any two of these would have to, the sum of the product of any two of these would have to equal 0. So if you can see here, what this demands is that there's at least one -1 or two -1 species anti-symmetrical relationships within this representation, whatever it is. Because if this one times this one, this would be 1, this would be -1, this would be -1, this would be 1, the sum of those would then be 0. Whereas this one, -1 times 1, no big deal, -1, -1. And so we can do this by inspection for this one, and so we can figure out that, well, again, all of these have to be an identity of 0, of 1. The sum of these has to equal the order. Sum of the squares of these has to equal the order, and so we can then figure out that the missing one would, the only way this would work would be if one of them is negative, and so we can take that one, and then would represent a -1 there and a 1 there. Right? That's the only way we could get these to sum up correctly. So this one times that, it has to be two negatives, and then you would figure out the missing piece. Right? Now there's a mathematical way to do this, and we'll look at a separate representation. But via inspection, it's fairly easy to do that with these. You could brute force it as well. Ask yourself what number times what would equal. But for a simple matrix like this, it actually works fairly well. Now additionally, we can come back and label these with our Mulliken labels. And so, again, the big ones are the C2 axis, or the principal rotation axis, and whether it's symmetric or anti-symmetric with respect to a mirror plane. So there's no inversion center or anything like that, so Girardi on Girardi doesn't work. And so we can look, is it symmetrical? So these are all anti-symmetrical with respect to the C2, so these are all B relationships. These would have to all be A, because they're symmetrical. And then we can talk about whether it's symmetrical or anti-symmetrical with the mirror plane. And so this one's anti-symmetrical, A2, A1, B2, B1. Right? And so these would represent the character table. Then we usually put them in order by letter and then symmetry. And that would generate our final form. Now, so those missing rules, those orthogonality rules, are really important in other representations as well, because when you sum things up, if you add a couple up, they'll cancel each other out. And so embedded within any operation, any reduced representation, is a series of relationships. And so you can actually pull out the reduced representations in a more complex transformation, which is what we're going to do. All right? So it's kind of the reverse of what we just did, where we just kind of eyeballed what we can actually do this mathematically and rigorously. Right? Again, I will not ask you to build a character table. I may ask you to identify whether something is symmetry, what the symmetry, the Mulliken label is for a symmetry species. Right? So, how we're going to use this. Okay, so, character tables, someone's done this for us. Right? And so we have this tables, all these tables in the back of our book. All right, so you actually look in the back of your book, there's a ton of character tables. Or just Google character table C4N or something like that, and C4H, and you can, or D4H, and you can find these informations. But there are a couple quick things that you can do. Right away, just from the symmetry table, you can say whether it's chiral or not. All right? If it's chiral, it can't have an SN axis. And there are a couple hidden SN axes. It's really obvious if it has an inversion center or a mirror plane, it cannot be chiral. All right? But if there's an S-axis of any type in there, besides a mirror plane, and it can't be chiral. All right, look, there is a sigma plane. Sigma, this material, regardless of what it is, cannot be chiral. All right, chiral molecules will have will not have an improper rotation axis. Polarity, again, polarity thing is that whenever there's a dipole in the molecule, if it's non-polar, the material will have it can't be polar if it has an inversion center, a mirror plane when the dipole is orthogonal to it, or a rotation axis. All right? And where this shows up in principle is really when the molecule is of the D point groups. All right? So these often have mirror planes and C2 axes. And so if you see a material that has a D point group, it's not going to be polar. It's not going to be able to support a dipole because of the way the symmetry elements. Again, those are relatively trivial but easy things to look at. You look at a point, this material, a dipole orthogonal to the mirror plane. All right, the question is do we have one? And so you'd have to look at the molecule. And so for this one, the dipole runs for the water molecule. It's in the sigma, the xz plane and the yz plane. Both of those encompass that dipole. And so therefore it is possible to be polar. And so this one actually is. If that was orthogonal, it was perpendicular, it would then be reflected in some way and balanced out, like CO2, for instance. All right, last and most important, and where we're going to spend most of our time, are vibrational and molecular orbitals. Symmetry allows us to determine the irreducible representations in vibrations for molecules and molecular orbitals, right? Using something called symmetry-adapted linear combinations, SALCs. So the SALCs, though, we'll talk about in the next discussion. All right? So first of all, we're just going to do a complete vibrational analysis for a molecule. You can talk about vibrational idea. You don't need to know how everything moves. You don't need to think about every single one of the vibrations. The reason for that is all of the vibrations transform as symmetry species within the molecule. And so the fact that it has a particular symmetry defines what particular vibrations are valid for the structure. Okay? So for a group of molecules, we talk about the degrees of freedom, something you've heard before. And for a non-linear molecule, the number of degrees, vibrational degrees of freedom is 3n minus 6, all right? Where n is the number of atoms. And again, this has to do with the rotations and translation. So that's what the 6 is. It is the 3 rotations and the 3 vibrations, or 3 translations when we talk about a vibration. Right? We don't think about it when something vibrates. If all the molecules are migrating this way, a vibration is when atoms are moving. All right, and those movements undergo transformations the same way as other things. And so if everything is moving in this direction, vibrationally, it's actually just a translation. Okay. And so we have to take that into account. So let's do this for water. Let's take a look at all the vibrational modes for water. And the way we're going to do this is we're going to cheat. Okay? We're going to, rather than think about, okay, let's think about how all the atoms are moving, we're just going to move all of them. All right? We're going to assign a coordinate to each atom. XYZ, using our standard format, right-hand rule. And then we're going to look at how those coordinates change. So rather than thinking about the actual atom moving, if an atom moves and it changes its coordinate, the coordinate will either be, it will change things. All right? So the way we're going to do it, again, we're not looking at symmetry relationship, we're looking at actually how the coordinates change. And so we can use a sort of shorthand to build up a collection of all the ways the atoms can move. So we're going to build up a collection of all the movements possible for the atom. Right? And this, again, within that symmetry representation, the way they move is going to be a sum of the irreducible representations. Assign a coordinate system, and then we're just going to determine how the element behaves, how the atom behaves. Okay? So we're going to sum up all of the changes to create a reduced representation given the symbol gamma. All right? And so this will represent a linear combination of the individual characters within a series of the reduced representations. And so we can extract those out to a sum of irreducible forms. We'll save that. We'll use a similar process for molecular orbital diagrams and things like that. And so what turns out that this analogy for vibrations, we'll extend it exactly to molecular orbitals. For the most part, we don't actually do this. All right? Someone has done it for us. But again, we're going to talk about the basics. We're going to go through how it works. All right. Again, look at the coordinates. Let's do a symmetry operation. Identity. We take a look at the identity. And if the atom moves, the character is 0. Right? So that means that it contributes nothing. So we have 3 atoms. And if they had moved, they would all contribute nothing to this symmetry operation. Right? If the atom is stationary, any axis that is unchanged is 1, and then any axis that is inverted would represent a negative 1. So for the identity, it's kind of trivial. Again, so for our identity, we're going to sum up we're going to do a reduced representation, we'll call it gamma. So for our identity element, we have our water molecule, we have all its axes, and then we rotate, so this one is 9. 1, 2, 3, 1, 2, 3, 1, 2, 3, identity, pretty simple. All right. Now, C2, if we rotate this C2, we find that the H's move, and so they contribute 0, but the oxygen, the z-axis stays the same, and the x and the y have been inverted. The atom doesn't move, it stays in its same location, it just rotates around that location, and so each one that moves represents a -1, and so we sum up all the characters, -1 plus a -1 plus a +1, character of -1, +1, +1, +1, -1, -1. We look at a similar analysis for the sigma xz. So for the xz axis, right, so that would be the plane that divides the two. So the xz axis, we see that the two H atoms move, and so therefore they don't. So these two trade places, and so those atoms have moved, and so therefore we don't consider those axes at all. So we only have to worry about the oxygen atom, and we see that the z and the x-axis stay the same, and the y-axis inverts. So the z is +1, the x is +1, and the y is -1, and so therefore that would be a +1. And lastly, the y-axis, the mirrored plane that contains the entire atom, all the atoms stay exactly where they're at. One of the axes is flipped, in this case it's the x-axis. This yz contains the molecule, and so the x-axis flips. And so therefore it is sort of the opposite. It looks just like this, except the x is now negative and the y is positive. But there are 3 atoms that do this, so +3. Right? So this represents the reduced representation for all the motion in the structure, all of the transformations. Within that are individual transformations. And so the way we get out that is by using this orthogonality rule. So the great orthogonality theorem basically says that because they are all perpendicular to one another, you can use information about the order and the character as a sum to figure out how many of those particular irreducible representations, how many vibrations have that particular, or translations have that particular modality. And so the way we're going to do this is to take a fraction 1 over the order times the sum of the number of operators in the class, so basically the number up here, which for this example isn't important, but for something like this, we'd say 2 times the number here. And this is often forgotten, so just be aware that you have to take into that symmetry the fact that there are 2 of those particular class times so whatever that number of operators in the class, in this example it's only going to be 1, times the character of the reduced representation, the thing we just generated. Remember, so this is our reduced representation. We're going to take this character and then multiply it by the character of the irreduced representation. Right? And so because of the orthogonality theorem, we know that some of these will cancel out, and this will allow us to look at only those that contribute. Like sometimes you'll multiply this all out and there will be 0, and that says that there are 0 of these particular type of irreducible representations within this particular transformation. Now, since we're doing a sum of all of them, all the motions, there's probably several that are there of each class. But we can look at very specific parts of the molecule. We can look at just one motion and say, oh, what's the symmetry? What operations are related to that? What is the what symmetry does it represent? And that's exactly what we're going to do. But for now, let's do it for the whole molecule. So let's do with respect to A1. All right. So we'll take a look at this symmetry representation A1. All right. So how many A1s are there? All right. So we'll take a 1 over the order. This case is 4. Times the sum of all of these other things. And so, multiply by the number in the class times the symmetry element, and then we go to our table. We go to our table, and we see that in our table, each of these are all symmetric 1, 1, 1, 1, and so the character associated with this will be 1. We can do this for all of them. 1, negative 1, 1, plus 1, 3, and 1. Again, this will be from our character. So this is our A1 representation. This is our reduced representation, and this is from our character table. All right. And so we can sum this up. We can see that this is 9 plus negative 1 plus 1 plus 3. 9 math. 9, negative 1, 9, 12. 12 divided by 4. So there are 3 A1s within this representation. And then we can do it for all the other ones too. Okay, so we have 3 A1s. And so let's try it for the A2. So on our A2 representation, it's 1, 1. And so for A2, that's 1, 1, negative 1, and a negative 1. And so we can take our reduced representation again, and 1 over 4 times. So in this case, this becomes 9, negative 1, negative 1, negative 3, 9 minus 5. So this will be an A2, the sum of which 1/4 of 5, 1/4 of 4, in this case 9 minus 4. 9 minus 5 is 4, 1/4 of that. So there would be plus 1 A2. Okay? So for A2, that will be equal to 1 representation. So this number equals 1. So that would represent how many A2s are in this reduced representation. So we're using the property of orthogonality to measure how many are on there. So we're basically multiplying this by the reduced representation for the unit, which has to be equivalent, and we're extracting them out in that sense. So we can do this for the next one, B1. Right? B1's character reduced representation in this case would be 1, negative 1, negative 1, 1. Oops, sorry, 1, 1, 1, negative 1. All right. And then we can do this representation again. 1 over 4 times 1, 9, 1/4 times 1 times the character times 1 plus 1 times negative 1, negative 1 plus 1 times 1 negative 3, 1, 1, 11. This will equal 2. 9 minus 9, 10, 11 minus 3 is 4, 8. 8 divided by 4 is equal to 2, so that would represent 2 B1s within the system, and then we can do the same for B2s. I'll leave this one for you to determine, and it turns out that there are, and if you do it right, you should get 3 B2s. Now this represents, so our reduced representation would represent the sum of 3 A1s plus 1 A2 plus 2 B1 plus 3 B3s. Okay. And so within that, that is all of the translation and motion of each of the atoms and their symmetry relationships. But within that, I mean, that's all of them. That's all of our motion. The vibrational motion, though, we have to take into account the 3 translations and the 3 rotations associated with the molecule. And you see from the character table that things that are translation, anything along the translation will transform as that particular element. So a translation along Z, it's not just orbitals, it's also motion. So Z transformed, motion along there transforms as A1. So I guess this way. And so that would represent the motion, the translation. And so that is that 3n minus 6 that we're talking about. So we have to take into account those motions. And so those are our 3n's. Let's do the minus 6. And so we take care of one of the rotations, A1. Let's see what else we got. We got the B, the x-axis is transformed as 1b plus a b plus a y, which would be a b2. And so those we would eliminate from our representation, and then we can do the same for the rotations, which is also an A2, a B1, and a B2, leaving us at the end with 2 A1 modes, and the A2 drops out. Subtract, there's no B2s, and 1 B2. So we would expect there to be 3 vibrational modes in this structure for the water molecule. 2 symmetric and 1 antisymmetric. So those are our expected vibrational modes for the structure. Now, to assign those modes, you would have to look at the actual vibrations. All right? But so what this allows us to do is, from just the structure, determine how many vibrations are valid. On top of that, because of other exclusion rules, we can talk about some that are IR active and some that are Raman active. And so we can use vibrational spectroscopy to do structure identification. So in this particular case, if the molecule has a center of inversion, the modes that are IR active could not also be Raman active. This does not have an inversion center, so it could be, we would expect 3 modes in both the IR and in the Raman. Right? The energy of which is we can determine, but that's not symmetry. So it's a little esoteric. I mean, it's a little esoteric way of representing this, but it is incredibly powerful. I mean, we can do this for almost anything. We can look at a structure and talk about whether or not a mode will be IR visible or Raman visible, just by looking at the mode, if we know what the mode is. Right? So for instance, let's take a look at an example like this cisplatin. Okay, cisplatin has vibrational modes that are related to water. Right? We can look at water and see that it is C2V, so is cisplatin. So we can look at the structures pretty easily and look at two of the vibrational modes. Right? There's a third one. There's a third one that we don't see. I think that's a WAG, actually. So this is vibration like this. Do the water dance. It's vibration like this, and I think there's a WAG like this. All right. The reason that this doesn't count as a WAG, that's a rotation. So, and this would be this symmetric WAG as opposed to the asymmetric WAG. All right, doesn't work. All right. So, regardless, we can look at the structure and we can talk about what transformation is what. We don't have to go through this complex process for a very simple structure. All right? And so in this case, we have the molecule going like this, extends out, extends back. Look at how it transforms. All right? With respect to identity, it's always 1, no big deal. What about the C2 rotation? If we rotate it, we can see that, if I turn around, all right, it's pretty much exactly the same. All right, so we can do the mirror plane. Again, the mirror planes in both directions do nothing to the symmetry. So this would transform as A1. So this vibrational mode where both of the atoms are moving away from the central atom, in our case of platinum, that would be an A1 transformation, and we'd expect it to follow all the rules associated with that. Conversely, if we look at the asymmetric transformation, we can see that right away it is asymmetric with respect to C2 rotation. Here, my left hand or right hand to you is up, and my right hand is down, left hand is down, well, whatever. One is down and one is up, and then if we do a C2 rotation, it's just the opposite, that's anti-symmetric. And so we could see that that transforms as B2. Right? And so we know that it's B2 because these are the only two vibrations that are possible here. And even if we just, okay, well, if it's B1 or B2 now, how do we tell? We can look at the mirror plane. If we know that that's within the YZ plane, we can see that the x-axis changes, and we can see that it's within the YZ, it is symmetric. All right, so we know that those are the two modes, the A1 mode and the B2 mode for cisplatin. We can do the same thing for other structures. We would expect that these, in the cisplatin, both of these would be both IR active, here's the A1, IR active things transform as the principal axes. Raman active things transform as the quadratic terms. And so we'd see that the A1 would have visibility in the IR and in the Raman. We can do the same thing for the B2 mode, IR, and Raman. So if we take a look at this one, on the other hand, this symmetric stretch, right, and both of them are stretching out, we can see that that transforms as A Gerardi, AG. That would be Raman active, not IR active. Whereas the asymmetric stretch, all right, it would be anti-symmetric with respect to the C2 axis, the principal axis. It's going to be symmetrical with respect to the y-axis because of the way the y-axis works. So it'll be symmetrical with respect to inversion on that one. And on the x-axis, which would be above and below the plane, it will be also symmetric. So symmetrical with respect, anti-symmetrical with respect to that, symmetrical with respect to the y-axis, so it's going to be B2G or B2U. And then we take a look at symmetrical with respect to inversion, so it would be anti-symmetrical with respect to inversion, and so it would be B2U. And so we know that this is a B2U, and we can see that B2U is IR active, but not Raman active. And so we would expect it to have these two stretches. One of them would be active in the IR, and one of them would be active in the IR. There's only 2 bands, but sometimes there are like multiple bands in the IR and then a decrease in the Raman. So you can use it to tell between different structures fairly easily from first principles, from just knowing the symmetry. And again, if something has both a center of inversion, none of the modes can be both IR and Raman active, and so you can look at whether or not. All right, so relatively complex, weighty subject. What we're going to do, though, is we're going to use this same idea to talk about symmetry-adapted linear combinations of molecular orbitals. And that'll be in the next talk, all right?